Okay, everyone, we're going to continue our look at your Chapter 5 practice test with question 12 here. So approximately 30% of the calls to an airline reservation phone line result in a reservation being made. So part A is, suppose an operator handles 10 calls. What's the probability that none of the 10 calls result in a reservation? Now, we've done a few problems like this already, so I think we're going to go through this a little bit quickly. So we have to assume independence to start off with. And if we want to know that the probability that none of the 10 calls are resulting in a reservation, we can say that the probability that we don't get a reservation in 10 calls is going to be the same thing as multiplying the probability of not getting a reservation on each of the calls. Now, each of the calls are independent, or we're assuming they're independent, so we can just multiply those probabilities together. So the next thing that's left for us to do is to figure out, well, what is the probability that a reservation isn't being made? So here again, we're looking at mutually exclusive outcomes. Either someone makes a reservation or they don't make a reservation. So the probability of no reservation is 1 minus the probability of making a reservation, and that's 1 minus 0.3, or 0.7. So then our probability becomes 0.7 multiplied 10 times together, or if you prefer, 0.7 to the 10th power. And that gives us to 0.0282. So if we take 10 calls and 30% of them will result in a reservation, then it's a pretty low probability that we get no reservations in those 10 calls. And I think part B, we've already answered that. What assumptions did we make? We had to make the assumption that the calls were independent. Okay. And lastly, what's the probability that at least one call results in a reservation being made? And if you've been watching the other videos, then you've seen me highlight this at least one call. Okay, actually, this entire phrase goes together. So at least one call results in a reservation, and we think about the complement of that, which would mean no calls were made in a reservation, resulted in the reservation. So the probability of at least one call, the probability that at least one call in 10 is a reservation, is 1 minus the probability that there are no calls made in a reservation. Since we calculated that in part A, we'll just put that number right in there, and we get a 97.18% probability that at least one call will result in a reservation. Moving on to question 13, we have Mayu Watanabe is applying to both UCLA and USC. She thinks that the probability that UCLA will admit her is 0.4, and the probability that USC will admit her is 0.5, and the probability that both will admit her is 0.2. So part A says to make a Venn diagram in a two-way table for the probabilities. Here's a good Venn diagram, and we'll call the left circle UCLA and the right circle USC. And let's see, we always start from the middle. So what's the probability that both schools will admit her? That's 0.2. Next, the probability that UCLA will admit her is 0.4. So 0.4 has to be the sum of this number, 0.2, and whatever is in here. So this has got to be 0.2 as well. Putting the decimal in the wrong place. Likewise, here at USC, 0.5 has to be these two probabilities, the almond shape and the moon shape, added together, and they have to add up to 0.5. So this should be 0.3. So the last bit is, what's the probability that neither school is going to admit her? And that's going to be anything that's not in here. So this is 0.2, 0.2, 0.3. This all adds up to 0.7. So out here, we got to put a 0.3. All four of these numbers need to add up to 1. So there's our Venn diagram. Let's look at a two-way table now. So here's a pretty simple two-way table, and we just need to put our numbers in it here. Just like before, we can start with the probability that both of them will admit her. So that's a UCLA yes and a USC yes. That's 0.2. What's nice about the two-way table now is that the probability of that UCLA is a yes, that's a single outcome, and we can put that in the total row. So the probability that UCLA will admit her is 0.4. Likewise, the probability that USC will admit her is 0.5. Now, using some subtraction rules, we can see that this has to be 0.6 if we want to add up to 100%. And if this is 0.5 here, that's also got to be 0.5 if we're going to add up to 100%. So we've already found the probability that UCLA will not admit her and the probability that USC won't admit her. Now with this 0.2 here, we should be able to use subtraction to figure out the rest of the numbers in this table. For example, USC yes is 0.5. 0.2 is UCLA yes and USC yes. That means 0.3 needs to be USC yes and UCLA no, because they need to add up to 0.5. Coming down this row, the probability that UCLA and USC admits her is 0.2. The total probability that UCLA will admit her is 0.4. So over here, for UCLA yes and USC no, that's got to be 0.2 because these two interior numbers need to add up to the marginal total. Likewise, in the UCLA no column, 0.3 and this number here have to add up to 0.6. So that gives me a 0.3 here. Notice how the numbers are the same in both of the charts. Which brings us to part B. What's the probability that neither university admits Mayu? So what's the probability of Once again, this is an AND probability, so we're looking at an inside cell. Since all the numbers are already probabilities, we don't have to do any division, although it probably doesn't hurt. 0.3 divided by 1 is still 0.3. So again, this AND probability means we're looking at an inside cell for UCLA and USC no, the intersection of both of them. Question C. What's the probability that she gets into UCLA but not USC? Translated symbolically, that's the probability of UCLA yes and USC no. Because it is an AND, we are looking for an inside number. So the intersection of UCLA yes and USC no is 0.2, making this probability 0.2. And finally, if Mayu is admitted into USC, what's the probability that she'll be admitted into UCLA? And the part that I want to highlight here is if she's admitted into USC, that is code speak for given USC yes. Okay, so we're assuming that she got into USC, so that's USC yes. Let's move this up here so we can fit everything. And this question becomes, what's the probability? Well, we don't know what the first part is, but we know the second part is USC yes. Okay, and then we can say the probability that she is admitted into UCLA. So this is UCLA yes. Okay. You've seen me do this in the other videos. I'm going to look at the USC yes row and only the USC yes row. Ooh, we've lost some of our numbers. Okay, that's better. USC yes, that is this row right here. So given that USC was a yes, what's the probability of a UCLA yes? Now that we've got that row done, we can say, well, what's the probability of a UCLA yes? And that is 0.2 out of a total of 0.5. That's 0.4. So if you wanted to see that symbolically, and again, I do encourage you to think of it this way, this is a probability of UCLA yes and USC yes divided by the probability of USC yes. And those numbers actually bear out quite nicely because we already have a UCLA yes, and a USC yes. We knew that that was 0.2 from right here, divided by the probability of USC yes, which is still 0.5. So, like we saw before, it's the exact same numbers, just taking a look at it symbolically. Depending on whether or not you have a two-way table will really dictate whether or not you use the graphical method, or if you by looking at the chart, or if you use a symbolic method like we just did. So that was our last two questions for this video, or I guess our only two questions for this video, numbers 12 and 13. We'll see you for the next one, question 14.